Welcome, everyone. So the purpose of this workshop series is to help frame for the healthcare audience, like what is deep learning? Like this is going to be a really big buzzword that you're hearing probably for a while now, and it directly integrates into things like large language models and artificial intelligence, right? So one of the sub goals of this first workshop is to kind of disentangle this terminology a little bit because it's becoming a bit convoluted, right? So the artificial intelligence, for example, actually encompasses a lot more than what people are now in the mainstream calling it, right? So we'll kind of define that and then moving forward. So the order and the way that these workshops are structured is that this first one is all conceptual, so an overview as digestible as possible for each of the main subtopics. So starting an overview of deep learning, moving into sequence-based modeling, so stuff like time series analysis in modeling, then moving into what are called RAG models, which is a way to communicate it in essence with things like large language models. The second of these little like dual workshops is applied. So this will be working within Python. So the way that I'm going to be doing it, it might be a little different than what you would do, but we would be giving out instructions on setting up a Google Colab space. So it's a free open source Python environment. But the idea is it's a kind of like a minimal and digestible version of that code. Of course, all slides and code notebooks are going to be available to you to utilize after the fact as well. Okay. So I'm going to share the slide deck for this workshop series and we can get for this specific workshop and we'll get started. Great. Can everyone see my screen well? Okay, excellent. I will be taking points in the workshop to get questions or anything along those lines. It is also possible that we won't finish all of this material based off of the pace and different questions that are having along the way. I generally find that this is okay. We'll either pick up where we left off, or there will definitely be a quick summary of this type of concept for the next workshop as well. All right. My name is Dr. Greg Chisholm. I'm an assistant professor of practice at the College of Information Science. So my general background and methodology that has been coming into fruition is kind of developing artificial intelligence, or rather these kind of deep learning and machine learning based approaches to solving complex problems. And one of the complex problems I'm addressing, within the next year or two, is thinking about things like patient pathways. So how do we disentangle pathways that individuals have gone through throughout their patient care journey? And how can we then infer how another patient might benefit from seeing those gaps in care, or perhaps seeing how care has been done for someone similar to them that they haven't done yet. So that's just kind of a broad stroke of one thing that I'm invested in. But I don't want to waste too much time on just myself. Let's get started. So our objective is to provide a theoretical framework for deep learning. So we're going to be focusing on kind of the core concepts of what are called neural networks, things like activation functions, and then kind of the broad stroke most common training strategies for dealing with these models, okay? And perhaps thankfully for some of you, there's no code today, right? So I want to keep this purely in kind of like a digestible theoretical framework, but hopefully everything can come across well. So when we go into the applied framework, you have a good starting point. So an overview of the specific topics that we're going to be covering. And yes, I know we all like code, but don't worry, we will have code next week and it's all code. So it'll be live coding. I will be coding with you. And of course, I can give you any references or information on how to code these different types of things as well. So let's think about the overview of topics. We're going to be first thinking about what is artificial intelligence versus what's called machine learning versus what's called deep learning, okay? We'll have a broad strokes introduction into deep learning and thinking about it conceptually. This will be the structure that goes into it, things like back propagations. This is how you can have the models train themselves over time. And then some of the very general architectures that are in place for deep learning algorithms, they don't all in their, I guess, face value look alike, right? And each has its own set of pros and cons. We'll also be thinking about different challenges in using these type of models. And then also along the way, we'll be framing this all in a healthcare and health sciences framework. We'll then have a summary at the end. So as a general overview of artificial intelligence, typically when you say artificial intelligence or AI, a lot of times you get people asking, well, you mean just that's ChatGPT, right? Well, yes, in a sense, but it actually is quite a bit more broad than that, right? So artificial intelligence has been around actually probably since the 50s or even before. It is essentially any type of algorithm or any approach that lets a computer have what would be considered intelligence. So how does a computer think? How does a computer solve problems? So anything along those lines would be considered in a broad category of artificial intelligence. The next subcategory that goes into this was developed probably more like really started hitting in around the 80s or so would be machine learning. So artificial intelligence is how a computer can perhaps solve problems and be programmed in a specific way to do so. Machine learning is how do we have a machine learn from information that we give it to solve specific problems. So a lot of times it could be we're giving it some information, we have a set level of outcomes that we want to achieve. How well does it go from input to output and accurately? We then move into deep learning. The simplest way to think of it is like machine learning kind of on steroids. The biggest thing is it's quite greedy. It can handle a lot of data, but it needs to have a lot of data. And complexity can be in the level of order of, hundreds upon hundreds of columns and millions upon billions even of rows, right? So there are some distinct differences in machine and deep learning and how it's prepared. We'll discuss those more intimately. But the gist is that deep learning has this kind of, if you've heard of a black box, it can take the data and give you the outputs that are desired. We then move into things called generative AI. So this is what is more commonly and colloquially considered AI amongst the general public. So that's where ChatGPT comes into place. So generative AI, a lot of times is taking, and it's largely a text-based problem. So it takes some large corpus of data, of literal text. So for example, ChatGPT takes this huge amount of information from the internet, and it's taking from what has been produced already. It is then answering your questions in a way that are logically derived from what has been done in the past, right? So it can create things, but it's all it's all contextually dependent upon the reliability, accuracy, and just overall quality of the corpus of data that's been provided for it, okay? Which is why you can see so many different problems prospectively. My general argument is that if you want to learn about generative AI and ChatGPT and things like large language modeling, a good framework is to begin with deep learning because it's the conceptual overarching, I guess, grandfather of these concepts. And in doing so, you learn some of the frameworks in place that cascade into generative AI, things like large language models. Okay. So let's first think about machine learning. It's perhaps what many of you may have heard more about or have a relative background in. It can be split up into three major clades. If you wanted to do it that way, you have the two biggest, most common are what are called unsupervised and supervised learning. Unsupervised learning, it's better to start with supervised learning. Supervised learning has a set human input that it's trying to aim for, right? So think a classification problem. You have a column that has pass or fail, a 0 or a 1 in it, or you have several categories that you're aiming for. It could be they're classified as 0, 1, 2, 3, whatever that might be. You have all a bunch of other features or columns, and you're trying to find the algorithm that best predicts what those outcomes are that you're targeting are from the input values, those input columns, right? The biggest thing to know from this is that there's a direct human input you're providing the outcome to look for. This is also true for regression algorithms, and it might not seem as clear as to why, but it's because in a regression, you're typically telling the model the shape or the actual the way that the relationship exists. So think a linear model, you're saying it's going to be linear. A polynomial model, it's going to be whatever order polynomial you're giving it, and so on and so forth, right? So there's still a direct human input, but that input is a little more indirect. It's not adding a column, it's saying this is the shape of the relationship that's going to occur, right? And then the model will fit that relationship to the data X and Y, and it will give you some level of accuracy on how well it did that, okay? So on the flip side, you have what's called unsupervised learning. This is more commonly utilized when there isn't a clear output that you're aiming for. So think you have really highly complex or multidimensional data, and you need to remove the noise, is one way to think of it. Remove anything that isn't really as important. So that's where you can do things like dimensional reduction, which is saying, give me, what number of dimensions of the data, or reduce it down to the number of dimensions of the data that gives you a certain cutoff of variation within the data set, usually something around 75% or more. So what you're doing is saying, here's 100 columns, reduce this down to 5 dimensions that encompass 75% or so, or however many dimensions encompass that. Typically it's around 2 or so, but it can really range up to even up to 10 plus, okay? The other way that unsupervised learning is commonly utilized is what's called clustering. So clustering is taking a bunch of columns and asking questions related to how similar or dissimilar are those values within the columns from one another in a broad pattern sense. So you define the number of clusters you want to create. Let's say 3 is a common one. And you're saying, cluster all of this information dimensionally down into these 3 or so clusters, right? So what's challenging is that it doesn't actually reduce the dimensionality of the columns, meaning that if you tried to visualize it, you still have 50 columns or something. You could then use dimensional reduction techniques to collapse that down to 2 dimensions, and then you could thus visualize what those clusters actually look like, okay? So kind of a really broad explanation of it. We're not going into each of the individual algorithms, but I want to at least have an idea of going forward what this is. Lastly, reinforcement learning, it's a little bit of a hybrid in a way, but the idea is that at different stages of the learning process, you're coming in as the human and reinforcing the algorithm in some way. You're saying, oh, you're not performing well, bump up your weights in this way, or oh, okay, maybe you're overfitting. Let's change the bias metric or something along those lines. So there is some direct human contribution in that component. Okay. Now, this isn't strictly a machine learning lecture, but I am open to questions on what you might have about any of these specific clades or classifications of machine learning before we move on a little further. And of course, either unmute or in the chat works as well. If you're interested on resources that help visually distinguish these types of models, feel free to contact me, or I can, an example of dimensional reduction. Yeah, principal component analysis is the most commonly utilized algorithm for this. So principal component reduction is using eigenvectors to reduce down. Yeah, so that's the most commonly utilized one. So as a reference, I want to show a table that might be useful for you. So I teach data mining and discovery, and I created a summary table of different machine learning algorithms, and then things like imputation. So an imputation is a way to take missing values or outliers and conform them to the standard distribution of that data. So it's a good overview of the different methodologies, their pros and cons, some example use cases, and then their methodology in Python. All right. So we like code. There's at least some examples of how to do these algorithms, a lot of these different algorithms inside of Python. So if that's useful to you, that's great. Otherwise, I will be building out a resource like this much more thoroughly in the future. Okay, so perhaps you're all here because you know why these types of topics are important, but um, thinking about why do we actually care about machine learning in the health sciences? What are the actual types of problems that it has and can solve? So it has played a very important role in solving different types of problems. For example, medical imaging and diagnostics. Machine learning is quite good, in particular classification, is quite good at identifying things like tumor cells in cancer patients compared to healthy tissue. And then it's also helpful for different diagnostics. So it can take commonalities in individuals with different diseases or conditions, and then it gives you sort of an insight into likelihood of an individual having said disease or illness. But medical imaging in particular has advanced quite a lot due to machine learning. Things like health economics and predictive healthcare. So this kind of gets into sort of a policy standpoint as well as a forecasting future need for care of individuals. So it has this great component that can help predict well, what is the burden of care that we're going to be seeing in the future? Ergo, how do we compensate for that in policy and in the money component of it, which is, of course, of quite important to policymakers. It's, of course, been extremely helpful in biomedical research and drug discovery. The deep learning component has been even more helpful in some way, I think, to this, especially like generative algorithms. So there's been generative AI that has created this whole new corpus of different types of drugs that can be possible or available. And then on the flip side, also a bunch of like highly poisonous and toxic things for people, but it speaks towards the ethics and proper use of these type of tools, right? But what's great is the machine learning even has been quite helpful in this regard. Of course, things like medical devices and robotics. Robotics makes sense. You're basically training robots to do certain tasks in an effective way. Medical devices, so this could go to anything that's providing electronic health records or anything or live records. And this could even be like wearables. So things like smart watches that get things like heart rate, or even have the ability to take some rudimentary readings. So there is there are some lightweight machine learning algorithms that are on the software for these devices that say, oh, you might be tachycardic or something along those lines. And of course, clinical natural language processing. So one way this can be summarized is you have a lot, like tons and tons and tons of text information. You have not only electronic health records, you have doctors scribe notes, you have policy information, you have this whole corpus. So it can help process that information and provide patterns and classifications for that language. This becomes even more powerful when you start discussing things like large language models. So in a very broad stroke, what does this look like? And I'm showing this because the direct deep learning comparison shows very specifically what's being cut out of the equation. In machine learning, you have something like an input. In this case, here's this car. You have feature extraction. This is the key thing here. The feature extraction is done by the humans in this case, right? So you are doing what's called feature extraction. You're going through and determining based off of your domain expertise or based off of like collaborators' expertise, what features actually matter, one, from the data, two, what features do we need to create as well to best approximate or best showcase what we're looking for. Okay, so then that feeds as inputs into, in this case, a classification model that is classifying if it's a car or not. And note that the visual for classification, that this would be an example of like a hierarchical classification model or a tree-based model that is going through a series of nodes saying yes or no and going down a tree for however long, right? So it's as a broad when to use it. You can use it for complex tasks and big data. So big data honestly means something different, I think, to literally everyone. But it could be quite large. You're still talking a couple gigabytes or so. That you also utilize many variables. So there's things like dimensional reduction, like I mentioned, that can go from hundreds of variables to relatively few. Okay. And then when the underlying formula or equation is relatively unknown. So if there are some components under the hood that you don't really know what's going on, so things like how do these variables group together? How can we actually think about this in a similarity or dissimilarity component? That's where machine learning can help as well with things like unsupervised learning. So kind of a broad, perhaps vague notion, but it is a good way to at least think about it. So this is also important on a how does it work framework, because it's important to know at least a couple steps. So the biggest is that there's a training and testing component, right? So training is typically 80% or so of the data. You're taking 80% of the overall data set, ideally with evenly split classifications, for example. And then you're leaving 20% of the data set to test upon, right? With the goal being that you don't really lose a lot of accuracy going from training to testing, right? It is a big red flag, for example, if your training data set's accuracy is like 90+%, but your testing accuracy is in the 60s or lower. And that's an indication of overfitting of the training data, meaning it's non-generalizable to the other data sets, right? And that can be a big problem. So if you have the data, training and testing, going into the machine learning algorithm, it can be split into those broad classes. For example, supervised learning, predictions based on both input and output. So you provide the input and the output. And then as a refresher, classification and regression are the two biggest clades in that case. Or unsupervised learning where you're group and interpreting based on only the inputs. You don't have any outputs in mind. So that could be clustering. Okay. So the biggest thing to note is this training and testing split does carry on throughout deep learning as well, which is why I wanted to at least communicate it now. And again, supervised trains a model based off of labeled data to predict outputs. Unsupervised finds hidden patterns in unlabeled data. Unlabeled literally meaning you don't have those classifications in mind. There are no labels to predict. Okay, so now we can move on to deep learning, but I do want to open again up to any questions about machine learning as a whole before moving on. So just in a broad sense, the types of deep learning networks that you might see. So I wanted this to be here as a way to show that deep learning inside of, under the hood has several different models that can be grouped within it. Yes, there's someone has to drop. I will send out, I'll make sure the recording goes out. Okay, so on to deep learning. It's important to know you might be seeing a lot of terms, things like a perceptron, feed fork neural networks, multi-layer perceptron, convolutional neural networks, and recurrent neural networks. And you're thinking, okay, great, well, I have to learn 5 terms. Well, in reality, it is all within deep learning. So that's why we will actually discuss, 3 of those today. But there are different use cases that are important for each of these, okay? So let's frame like we did with machine learning. Why do we actually care about this in the health sciences, right? So machine learning can already do a lot of really great things. What can deep learning do? It can typically achieve a higher diagnostic accuracy than ever before. So yes, machine learning can help with this. Deep learning is even more accurate. So like I said, remember, it's machine learning on steroids. It's like a leveled up version of it. So in this case, higher accuracy, which is awesome. We want that. It's used in a lot of critical healthcare applications. So disease detection. Think, the next global pandemic that we have, we want to have tools out there that can actually predict when this is happening more effectively, but also in direct disease detection. So whenever we have diagnostic tools, for example, that are trying to detect disease. It was developed broadly in the 80s and wasn't really widely adopted because of limited labeled medical data. So there wasn't medical data that could be utilized for this type of an approach as well. But the biggest limitation was computational power, right? These are really greedy and really computationally expensive models. So now we're in an age where you do have access readily to things like GPUs, which can hold a lot of internal memory. versus just CPU power, which has kind of a more limited amount of memory. And this is literally of an order of magnitude. Like one CPU can have, I think a max, it gets up to like 128 gigabytes of internal memory, whereas GPUs can have 10,000 plus gigabytes of working memory, which is quite amazing. So today we have vast sets of labeled data sets, like millions of medical images, so that if you wanted a direct example of what that would look like. So we have tons of these really highly accurate labeled images for diagnostic purposes, so that enables really high accuracy training in these models, which then can broadly generalize as a tool that can be used diagnostically. And then, as I was mentioning, we have high performance GPUs and cloud computing that can power deep learning effectively and efficiently in healthcare, right? And the key is much more inexpensively than back in the 1980s when, I mean, I couldn't even imagine how much a GPU would have cost back then. So let's go back to that framework that we had seen a little earlier on machine learning and think about the car. So then if you notice, the biggest difference is that it's much simpler, right? So the input is still the car, the output is still whether or not it is a car, but the actual component that is doing all of the work, the model itself, is doing both feature extraction and classification. So this has pros and cons. It increases the likelihood that really complex and unpredictable patterns can be disentangled. So things that humans actually cannot actually fathom. I like to think of it as a global perspective versus like a universal level perspective. We can perhaps fathom the globe, like the Earth, but we have a difficult time fathoming what's out there in the universe. So if we imagine that as our analogy, this big black box then is going in and doing all this for us. So the con, of course, is that it's less interpretable because we don't know what those features are going into the model, right? So that can have a huge problem, but it's unfortunately a necessary evil when you're talking about highly complex and really important questions that need high level of accuracy to answer. I will say that on the horizon, there are a lot of tools that are helping look under the hood on how these models work. And that does help with interpretability and then the overall understanding for how these models work. So I would give it a little bit of time, but I think we'll have a better understanding of what's under the hood soon. So like with machine learning, how or why would you use deep learning, or when rather? You would use it for what would be considered highly complex tasks that have vast amounts of data. So it's, like I said, a leveled up version of what we saw before. Complex, highly complex, large amounts, vast amounts of data, like terabytes of data in this case. And when you would perceive really intricate patterns that cannot be disentangled as easily from a human doing feature extraction. It can be quite easy for a human to just oversimplify things, for example. And then also when traditional methods of machine learning struggle to define the relationships. So if you find that the accuracy is really poor or that the relationship just isn't possible to be defined in what would be considered, like a two-dimensional space, like X and Y, then yes, it's time to start leveling up the model that you're utilizing. Okay. So to directly compare side by side machine and deep learning, we see again that the biggest difference here is that there's this weird kind of like cross-sectional node thing going on, this network that's happening in the deep learning that isn't necessarily happening the same way in machine learning, right? So this will segue right into where we discuss what that framework and structure actually is, okay? But note the overall structure of how the pipeline looks is simpler. However, it is, of course, much more complicated under the hood. So in the machine learning versus deep learning categories, deep learning is actually what we considered a specific type of machine learning, right? It's a more advanced and very specific overall structure to how it works. And machine learning features are pretty much manually extracted from things like images to develop something like a classification model. So you're going to have to manually go in and determine, well, what are the features of import in that image? Whereas in deep learning, it's going to look at those images and say, yep, I can figure it out myself. At least a very kind of a perhaps oversimplified way of thinking about it, but you can think about it in kind of those broad strokes. Deep learning uses what's considered end-to-end learning, where neural networks are learning directly from that raw data to perform classification. So that is what that framework is literally called, end-to-end. First, the end is input, the other end is output. There's nothing else in between. It's learning all along the way. And then deep learning algorithms improve with more data, while traditional machine learning models typically plateau. So there's a limit to how much improvement you can see in machine learning models for specific tasks, whereas always more data is better in deep learning. Like I've mentioned several times, and what I want to try to convey, they're quite greedy and they need to have really complex data. Oh, except in clustering, you don't dictate grouping to you. No, Randall, so you do not dictate the grouping. However, you still do feature extraction and selection. So there is a stage of that where, so let's frame it as there are two different versions of that question. Version one is, I got this data, I cleaned it up. Now I don't know I don't know how to classify it next, right? So you can use clustering to create those classifications for you, right? And then that's now the input for those models. That's kind of one version of that. The second version is similar. You're still getting that same output, but the input you are utilizing is being pared down based off of your domain knowledge, perhaps, or what you have known from the literature that says, well, these features are good approximates of what we're looking for. So let's create a new column or something along those lines, right? So you still have direct input. And that's the key difference between clustering and what the deep learning, I guess, version would be. But you're correct that it does have that similarity that you're stepping away a little bit. But yeah, the feature engineering component you are doing, correct. Thanks for asking that question for clarification. Okay, so finally, what are we looking at with deep learning? And hopefully we can pace this along pretty well, but as I mentioned before, I go over pretty much this component of the lecture in a summarized fashion next time as well, if we, for whatever reason, get cut off. Yeah, finally. But there's still no code this time. So next time, lots of code. I'll be live coding with you along the way. Okay. So let's start by thinking about what's called an artificial neural network, right? So this is getting into that structure that we saw, that web of network nodes that are interconnected with one another. Artificial neural networks were termed because at the time they were a hypothesized way that our brain works, in essence, right? So it was analogous to how our neurons are communicating with one another. Of course, we know that the reality is much, much more complex, and that's not really the case. But this is just you can think of it as a vastly oversimplified computer brain, right? So what's happening in this case is we have broad classifications of layers. Each of these vertical lines of dots are different layers along the pathway from input to output, right? Literally starting with an input node layer. So that's where inputs, 1, 2, 3 are coming into play. Inputs 1, 2, 3 could literally be column names or something like that. It's moving through what's considered a hidden nodes layer. So again, now we have our first black box. This is, a simple network, so it doesn't have multiple layers. But that hidden node layer is doing some transformation based off of what are called activation functions, which we'll discuss. It then produces the outputs that you want, right? So in this case, we're moving from 3 or more inputs to 2 outputs. So our 2 outputs could be a 0 and a 1. So it's a classification output, success or a fail, tested positive or negative for a diagnostic tool, anything along those lines, okay? If these dots are nodes, like in any network, these sticks, these arrows are links, right? So the arrows are linking the nodes together, and it's typically a fully connected node or a fully connected network from one layer to the next. So they're all kind of communicating forwardly to the next layer. Each of these nodes are also what are considered neurons. And I think I have another slide that'll discuss this a little bit further, right? So neurons literally with translation to how people thought our brains worked. So in this case, this is a common interpretation of what would be considered this neural network, and it is at the heart of deep learning. A neural network in this frame kind of is that bridge between, like to this level of sophistication, is that bridge between traditional machine learning and deep learning, right? So you can still do an artificial neural network and still not quite be what's considered deep learning, right? Meaning you're still doing all the feature extraction. So let's start with that. So that was a simple neural network, and we'll just compare that then to what deep learning neural networks look like. Okay, so if our simple neural network has, and I don't like using the word simple, it just means that there aren't multiple hidden layers. That is the simplified version of it. You have an input layer, goes to one single hidden layer, which then produces outputs. Okay. A deep learning neural network is much more sophisticated. It has several layers, right? So you can imagine how quickly the actual outputs will become uninterpretable when you're going through multiple hidden layers that are doing some transformation based off of a function, and then producing something that then is transformed again and again and again until you hit outputs, right? So that whole process inside of that hidden layer black box is a lot of times indecipherable. Whereas, for a simple neural network, you can probably understand what's going on because you know that it's just one layer of functions transforming the data from input to output. So it is more interpretable. So let's break down the components. I think this is one of the bigger goals of this portion of the talk or the lecture, is to try to disentangle what the components are, because when you start hearing these terminologies of like, what's an activation function? Well, what are they actually talking about when they're doing back propagation or whatever? We can actually look at that visually, what that more or less looks like. We have neurons, layers, which have input, hidden, output, activation functions, which are basically what takes the data and moves it between the layers, like the things that are happening to the data, the transformations. We have weights and biases. All right, so we've already briefly mentioned neurons and layers. I've said the term activation function, but I haven't described them. Okay, let's start with neurons. So as a refresher, the neurons are those individual nodes within the network. Okay. So they are, in essence, the building blocks of neural networks. You have several neurons that can go, in particular, however many number of input neurons you have. You can have an amazingly complex number of hidden layer neurons that are interwoven with each other. And then, of course, you have whatever the number of output neurons that you're looking for are. So those neurons that are taking information from the final hidden layer and then converting whatever into the output that you need. Each neuron performs what's considered a weighted sum of inputs, followed by an activation function. So we're starting to get a little meaty here. Weighted sums of inputs mean that we'll discuss weights. It's a way in which different transformations are made along those pathways, right? So each of these little links have a weight to them. And we'll also discuss activation functions. So layers, again, input layer in blue, that first layer, hidden layer in the middle, however many number of these yellow layers here, these nodes, output layer, green. Data enters in the beginning, gets processed in the middle, and produces the result and prediction at the end. Okay, so let's visually think about what an activation function is. And I kind of lied. There is code in here, but it's hidden. So I produced outputs from code of different highly common activation functions within deep learning networks. So these are functions that are basically being performed at these links at different points of the network. So they're taking the data, running it through these functions. So think of it as you're going from 0 to 1, perhaps, of your output or wherever it's being transformed to along that pipeline. These activation functions are saying probabilistically, when you hit this threshold, it's this class. When you hit the other threshold, it's another class, right? So a sigmoid function is quite common for this, where that inflection point, kind of where we're converting from 0 to 1, is at 0.5, meaning you have a 50% probability of your input leading to one or more, or to one or the other output. Ideally, it's shifting towards a 1 or a 0 in that sigmoid. And then softmax, for example, is the sophisticated sigmoid. And think of it, it handles multiple, it handles more than 2 outputs. Sigmoid has to be a 0 or a 1. Softmax can handle however many number, basically 2 up. And then the ReLU function has a basic, what it is attempting to do with classification is it performs nonlinear breaks in the data highly effectively. Hope we have some questions. Yeah, good question, Bruce. It's exactly like logistic regression. So that's why it's probably familiar. The sigmoid activation function is what's under the hood in logistic regression, right? It is probabilistically, so if logistic regression is a classification algorithm that asks along this sigmoid pathway, is it a 0 or a 1? And the closer it is to that 0.5 point, the harder it is for the algorithm to distinguish the two classifications, right? Whereas you ideally want them to be quite separable between 0 and 1. This is notable that it's a linearly separable thing with logistic regression. Typically, ReLU is also pretty typical of that. But for reference, if you're interested in the formulas for these, I won't go over them, but it's essentially a max value from 0 to whatever x ends up being. The characteristics of ReLU, so characteristics are helping you think about when to use them. They're quite simple and fast to compute. They are keeping positive values, so that helps the networks learn better. When there are more negative values in the deep learning networks, it can cause penalties to be too severe, so you can lose some of the accuracy. It slows them down. That's kind of one way to think of it. It really, the more negative bias that's being put against each layer, the more difficult it is for that to be recovered. So they're widely used in hidden layers of neural networks because of these characteristics. So what are they really great for? Deep learning networks for image recognition. So they're quite good at this, right? And I'm not mathematically inclined enough to say why exactly. I just know that from the literature, this is typically what's utilized because of how fast the algorithm ends up performing, right? Sigmoid is, the formula ends up being 1 over 1 plus e to the negative x. That's what the actual formula ends up being. The characteristics are producing binary decisions between 0 and 1. So that's ideal. That's what it's really great at. When in reality, it can't really do anything else. It, however, can slow down learning for really extreme inputs. So when the input values are really high or really low. So why does this matter? It matters because you have to, so the algorithms will transform the variables to reduce this penalty, at least with deep learning. This is really great when you're having a binary classification task. So you can assign, sigmoid layers can be assigned at the final layer of hidden layers in neural networks, right? So you're saying, all right, well, now I want you to turn it into a 0 or 1. Softmax, I like to think of it as a much more advanced version of sigmoid. So the formula looks very similar, except there's a summation. It basically is saying the summation from 1 to the n number of outputs. That's kind of a way to think of it. So that's why it can go up to n number of variables. The characteristics, it can turn outputs into probabilities that sum to 1, but it doesn't have to be a 0 or a 1, like the sigmoid does. So that's what's great for multi-classification problems, is each of those classifications get some value of probability, and that sums to 1. So it means that, let's say you have 3 classifications. Classification number 3 has a probability of 0.9, so it's much more likely than the other 2 classifications are 0.05 or something like that. So that means that that value would have been the 1 or the 0. So it's essential when you're dealing with multiple outcomes. So image classification with many categories, for example. If your classification isn't just cancer or known cancer, for example, this is where softmax is highly effective. So then you might be asking, how do I choose? I have this link embedded in my slides here, which for reference, this slide deck is live. So this is this specific slide in the chat, but you can go to, it's an HTML. You can go into this little menu here and go back to any point of my lecture. And I did just see a question. So when you say many categories, do you mean features or outputs? Many outputs, many outcomes. Yes. So more than 2 outcomes. Thanks for that clarification question. Okay, so I try to frame a lot of these topics in the so what. So why do I care about this, right? For activation functions, their importance in neural networks are that they are essential for dealing with nonlinearity. So the linear problem's easy. You throw a perceptron out there, it's going to put a line in the middle of linearly separable classes, right? That's pretty unrealistic in most cases. In most cases, real data is nonlinear when you're trying to classify something. You need to have some squiggly line or multiple breaks in the individual classifications. So they enable the networks to tackle complex tasks like image and then speech recognition as well. It helps with this layer-wise learning. So each layer can learn different features of the data. And it does this because each layer has its own activation function. So it's being tweaked in a different way. So then the next layer is learning from inputs from the previous layer. For training dynamics, the activation function is impacting network learning efficiency and speed. So the one that you choose will have a high influence, likely, on how fast that algorithm is performing. In medical applications, it's really key towards deep learning, accurately analyzing and predicting medical data. So things like diagnosing diseases, forecasting patient outcomes, or capturing really complex biological relationships. Okay, let's move on to weights. So the weights are another term for the links. Okay. The weights are individual values that are assigned to each of these individual lines here. So typically they're random small numbers. I think, yeah. They transform your input data inside of the network's hidden layers. So each layer has its own set of weights that are transforming the data before they're going into the next activation function, basically. So the purpose of weights are to help go from the input and then learn effectively and efficiently throughout the way into the output. So when the weights are calibrated effectively, the speed and accuracy of the algorithms are quite high. So they indicate the strength of the connection between the nodes. That is the practical sense what it is. So like I said, they're initially small random values. So that's where the stochastic gradient descent algorithm comes into play. There's a link to that in this slide. Biases can be imposed on individual nodes. So biases are a way to ideally skew the resulting transformations away from undesired outcomes, okay? So there are extra parameters that shift your activation functions. Think a lot of functions have parameters. You need to tweak them. That's what these do. They can allow neurons to activate even if the input is 0. Even if what they're receiving is 0, it's still activating and doing something with the data. They help models fit data more effectively. It's a way to think of it. Okay. So I'm going to have to I'll have to summarize some of this. So there's a difference between what are called batches and epochs. Data batches are you are chunking the data into multiple small batches. So if it's a really complex set of data, you are chunking them where you have inputs and outputs of whatever varying amounts. So in this case, blue and orange are our two outcomes. So you can have however many inputs from these batch layers. They're running through what are called epochs, right? So it starts, there are no predictions yet. The batches are passing through the model. This is one batch that went through until all of your batches run through. So one epoch is one complete path through the data. So note you have multiple batches possible because you're chunking your data up. You can also have multiple epochs, meaning you have multiple runs through your data because it's learning each time and tweaking the model at every output. So samples versus batches versus epochs. Batches per epoch ends up being the data set size over the batch size. One sample is one row of data. Batch size is the number of samples processed before updating the model. Epochs are the number of complete passes in the training data set. So then we have the epoch finish here. That's one pass through the data. Okay, I want to stop here. We're getting to where it's going to be very complicated anyway. Ideally, this would have been like an hour and a half, but I want to open up for any last minute questions before moving on to the next workshop. And I will continue this on. I might even record a separate video myself and then have it uploaded to complete this. The difference between activations and weights. Activations are taking, yeah, okay, so they look the same. Inside the node, that process of moving from one layer to the next, there's an activation function. And that function is changing the input from one layer into the output of the next layer, right? So that input could be 0 to 1 or something, or whatever the outputs of each function are. The weights are the parameters within that activate, or the weights rather, have to do with the strength of the connection between the nodes. So smaller weights mean that whatever the output of the activation function, if it's a low number, the impact on this node moving to that node is lower. So you can impose essentially a bias on how well connected the individual nodes are. Hopefully that's a little helpful, but it's a complicated concept. So I'm going to pop into breakout room 1.
Okay. Thank you, Greg.